Okay, I thought it might be helpful to address some of the most common misconceptions that I've seen in the Hawks problems. So I'm going to focus in just on the misconception portion of the problem. If you want to see a step-by-step solution to any of these problems, just get a screenshot of that and then send it to me, and I'd be glad to make a more complete video for that particular problem. So let me dive in. One thing I'd recommend that you do is, as soon as I flash a new problem, pause it real quick and acquaint yourself with the question, and then unpause and listen to what I address in that problem. So for this case, we're looking to see if we want the mean, the median, or the mode. And it's talking about the color of cars. So it really depends on what data type we're talking about here. And car color would be a qualitative or a nominal type. And when we're dealing with that kind of data, the mode is really what we need to go with. So we do have qualitative here. This preferred color or quantitative with outliers would go with median if that was the case for the data set. And if it didn't have outliers and it was quantitative, that's when we would want the mean. In this case, we have 6 actual data points, and we want to construct a 90% confidence interval for the mean. So the first misconception, I think, or the problematic point is what kind of procedure to use, a Z procedure or a T procedure. Because if you're using the calculator or SPSS or even Excel, you really need to know which of those two you're going with. And in a case like this, where we just have the sample data and we're constructing a confidence interval for the mean, in other words, there's many more data points, then we need to use a T procedure, unless somehow we have the population standard deviation, which we don't in this case. So I would just plug this into your calculator, these data points, to get the sample standard deviation. And the sample mean is what we need to do in step 1. Step 2, we would get that sample standard deviation. And email me if you don't know how to use the calculator to do that. And then the critical value, I think this could be a stumbling point. Let me hit that really quickly. So we have 6 data points. So since it's one sample, the degrees of freedom would be 5, and we want a 90% confidence interval. So on our T table, that means that 10% of our area would be in the tails. Confidence interval for the T procedures here will always be a two-tailed test. And we want 10% total area in the two tails. And we have 5 degrees of freedom, so 2.015 would be our critical value. And then we could either use that in the formula, or we could directly use our calculator here to get the confidence interval. So I think overall people would realize that this is a one proportion test or one proportion interval. The thing that trips people up on a question like this is the fact that we have 273 oil tankers. 194 did not have spills, and we want the proportion of oil tankers that had spills. So the thing we're looking for is actually the opposite of what's given to us. The easiest way to do that is just take care of it in the very beginning. Take 273 minus 194, and that'll be the number. 79 will be the number of oil tankers that did have spills. That's a horrible. I hope we don't have anywhere near that proportion of spills. But then you can use that 79. That can be what you use for the rest of your problem, whether you're using a formula or the calculator itself. Most important, just subtract that from the total number to get the number that had spills. The other thing here would be when you construct the 85% confidence interval, if you're using a calculator, you'll probably naturally get this as long as you subtract the 194 from 273. But if you're not, where do you look on the table? So we go to two tails, it's tricky here because the area and two tails would be in between these. And this is where it's important to realize we're not doing a t-test in this particular case. We're doing a proportion, and we have the requirements to do a z standard normal table. So since we're doing that, we would go to negative infinity to z. We would go to 15% divided by 2 would be 0.075, and that's what we would look for. We would do the negative infinity, negative z. We'd be looking for that 0.075. So negative 1.44 would be the critical z value, or positive 1.44. In the formula, actually, it gives you the same answer either way. Okay. So I think in this problem, the biggest thing would be identifying the fact that we're dealing with a binomial distribution, because we're talking about there's either two situations. Either they receive a magazine subscription order with an entry form, or they don't. And so to do that, we would grab the binomial cumulative. Cumulative means we're going to take all the situations that 0, 1, 2, 3, all the way up to 9. We want the probability less than 10. So anywhere between 0 and 9 is what we want. Our n value would be the total amount of trials. In this case, it's 14. And we want all the way between 0 and 9. And the probability of success here is 0.6. So we're grabbing that number here. The word cumulative means we're totaling up all the way between 0 and 9. So we don't have to do that manually. The table will do that. It tells us 72.07% of the time it's going to be 9 or less here. Okay, this would be a one sample proportion test, and we could use a z table. So if you're doing it through calculations, use the standard normal table. It also could be easily typed into the calculator. I think one part that could trip people up here would be this more than 48%. So when you're typing it in the calculator, make sure that your alternative hypothesis is more than whatever the number, more than the 48%. Okay, for this one, there's a couple places where people trip up in this type of problem. We have two samples here, and we're looking at their means, comparing their means. This line right here is pretty crucial. Because we're assuming that the variances are not equal, we don't want to do this pooled variance idea. And it also means that for the degrees of freedom, instead of adding these two numbers and subtracting 2, that's what we would do if the variances were equal. Because they're not equal, we're going to find the smaller sample size and subtract 1. So we would be looking up on the table 11 degrees of freedom. So it'd be the t-table. Because we don't have population standard deviation, we need to use the t-table here. And we would be looking up 11 degrees of freedom for that 80%, which means 20% in the two tails. To do the standard error, I think the best way is really just to use the formula. This is one that if you're focusing solely on the calculator, there are ways to do it. It's not quite as obvious. Let me show you the formula. Okay, so that standard error, the confidence intervals are basically our point estimate, our best guess at the population, plus or minus the critical value times standard error. So when we're assuming that they're unequal, or we're not assuming that the two variances are equal, or the standard deviations, this right here, this portion is the standard error, not including this. This is the number of standard errors that we're going to use to create the error margin. But this right here in the square root, including the square root itself, is the standard error that we would be using for this problem. And then constructing this, you could either do that on the calculator or using the standard error and the critical value you just found. If you are using the calculator, make sure, again, for this part, when you're filling out the calculator, it'll say something about pooled variances, and you do not want pooled variances. If you're assuming that the variances are equal, then you can pool them. Pool just means put them together into a single variance. But since they're not equal, you would want no on that option. Okay, this one, maybe I will go through real quick. The expected value, really just we have to figure out what's the chance that we will have two cards without replacement and both cards are spade. So the chance of getting one card without replacement being spades is 13 out of 52, or you could just put 1/4. That would be perfectly fine. And then after you've chosen that card, the chance that your second card would also be a spade. Well, there's 12 spades left out of the 51 cards. So multiply these. That'll give you the chance that you would win. So you would multiply that chance that you would win times 225. And then you would subtract the chance that you would lose, which would be 1 minus whatever this turns out to be. 1 minus that is the chance that you're going to lose. And you'll multiply that chance times 12. That's going to get subtracted from the chance you win times 225. And that's going to give you the expected value of your bet. Then what you can do is just take that number and multiply it by 738. Over time, on average, that's how much you would expect to win or lose using this type of wager. Okay, two things to note here. Again, we're given the variance. We would need to take the square root of that to get the standard deviation. The second is that this variance that we're given is coming from the population, which means we would use a Z procedure for this problem. And again, we have, maybe not again, we have the sample mean differing from the true mean by more than 158. So just to draw a real quick picture of what's happening there, you have the mean here of 19,695. And you want the area out in these two tails. So use the formula to figure out what your Z value is here. Use the standard normal table to figure out, or the on your calculator to figure out what this portion is, and then double it. All right, so here we have a T confidence interval, and the reason we know it's a T and not a Z is because the standard deviation we have is the sample. We do not have the population standard deviation. So because we have the sample, we have to use a T procedure, and that would be then 99 degrees of freedom, because our sample size here is 100. And if I didn't work it out, but if this 1200 falls inside the low and the high points of our interval, we would fail to reject. If it's outside of those two numbers, if it's either less than the lower one or more than the higher one, we would have reason to reject. So falling outside of the interval, we would reject the null.